Ever wondered what existed before the universe came into being? From the dawn of our species, we've looked to the skies and pondered our place in the grand cosmic scheme. Our curiosity has driven us to explore, to understand, and to make sense of the seemingly inscrutable mysteries that lie beyond our earthly confines. Enter the Big Bang Theory, a cornerstone of modern cosmology that has been a constant source of fascination for both researchers and the curious alike. The Big Bang Theory posits that our universe, in all its vast and intricate splendor, originated from an incredibly dense and hot state approximately 13.8 billion years ago. From this singularity, the universe expanded and cooled, eventually leading to the formation of atoms, stars, galaxies, and all the celestial bodies we're acquainted with today. But the Big Bang Theory isn't just about the birth and evolution of the universe. It's a narrative that has shaped our understanding of time, space, and matter. Yet, for all the answers the Big Bang Theory provides, it also raises one of the most profound and puzzling questions: what existed before the universe came into being? This question has perplexed scientists and philosophers alike, sparking countless debates and conjectures. Was there another universe before ours, a sort of cosmic cycle of death and rebirth? Or was there simply nothing? An infinite void devoid of time, space, and matter. As we delve deeper into the cosmic past, we find ourselves in largely uncharted territory. Our current understanding of physics breaks down and we're forced to confront the limits of our knowledge. It's a humbling reminder of the vastness of the cosmos and the mysteries that still await our discovery. So, what did exist before our universe? It's a question that continues to challenge our understanding of reality and pushes us to the very edges of scientific exploration. We may not have the answers yet, but the pursuit of these answers is what drives us forward. Dive with us into the journey of the universe from the very beginning. The Big Bang Theory, a name that you've probably heard before. Now, what exactly is this theory about? Well, in the simplest of terms, the Big Bang Theory is the leading explanation about how the universe began. Let's take a step back for a moment. Imagine a very hot, dense point, almost infinitely small, also known as a singularity. Now picture this point expanding rapidly, not just expanding but growing, cooling, and eventually forming everything we currently know in our universe. That's the Big Bang Theory for you. About 13.8 billion years ago, this singularity began expanding and stretching out. It's important to note that it's not just the matter within the universe that's expanding, but the universe itself. Think of it like a balloon being inflated. As you blow air into it, every point on the balloon's surface moves away from every other point. Just like this, every galaxy in the universe is moving away from every other galaxy. As the universe expanded, it cooled down. This cooling allowed for the formation of subatomic particles, and eventually, the atoms that we know today. These atoms grouped together to form clouds of gas, and eventually stars, galaxies, and everything else we see around us. However, the Big Bang Theory doesn't suggest that there was nothing, and then suddenly, bang, there was something. No, it's more about how the universe went from being extremely hot and dense to the current state we see today. It's a theory about the development of the universe, not its actual creation. You might be wondering, what about the evidence? How do we know this theory holds water? Well, there's a lot to talk about when it comes to evidence. For instance, we have the cosmic microwave background radiation, a faint glow of light that fills the universe and can be detected in every direction. This radiation is thought to be the heat left over from the original Big Bang. Then there's the abundance of light elements. Scientists have found that roughly 75% of the universe's mass is hydrogen, and about 25% is helium. These proportions match the predictions made by the Big Bang Theory. The Big Bang Theory also explains the large-scale structure of the universe. The galaxies we see are clumped together in a way that fits with the idea that the universe started out as a hot, dense state and has been expanding and cooling ever since. The Big Bang isn't a theory of the beginning, but a pathway to understanding the universe's history. It helps us piece together a story of how the universe developed over billions of years, from a tiny, dense point to the vast cosmos we know today. It's a fascinating story, one that's still being written as we continue to explore and understand the universe. So what was there before the Big Bang? Well, to answer that, we first have to grasp the idea that our understanding of before is based on the concept of time as we know it. However, if we subscribe to the idea of a timeless universe, then the concept of before may not apply at all. Here's an analogy. Imagine you're on Earth and you decide to start walking north. You keep walking, and eventually you reach the North Pole. Now, if someone asks you to go further north, you'd probably give them a puzzled look. There's no north beyond the North Pole. Similarly, in a universe where time began at the Big Bang, there's no before the Big Bang, yet this doesn't stop our curious minds from exploring the possibilities. Scientists have proposed several theories about what might have existed before. One such theory is the quantum bounce. It suggests that our universe is just the latest in a series of universes. The previous universe contracted due to gravity until it was compressed into a tiny speck. Quantum mechanics then caused it to bounce back and expand again, giving birth to our universe. Another theory borrows from string theory and proposes a parent universe that gave birth to our universe. This parent universe existed in a higher dimensional space, and its three-dimensional brain collided with another, causing the Big Bang. Then there's the multiverse theory, which suggests that our universe is just one of an infinite number of universes, each with its own Big Bang. This theory implies that there could be countless other universes, each with its own laws of physics. While these theories are fascinating, none have been proven definitively. They're all based on our current understanding of physics, which is constantly evolving. And who knows? Perhaps in the future, we'll discover a new fundamental law of physics that completely changes our understanding of what came before the Big Bang. While it remains a mystery, the question itself opens up a realm of fascinating possibilities. Imagine a moment, a fraction of a second, when the universe was born. In the beginning, there was a singularity, a point of infinite density and heat, where all the matter and energy of the universe was compressed into a space smaller than an atom. This was the state of the universe at the moment of the Big Bang. But what happened next? What were those first moments like? Immediately after the Big Bang, the universe began to expand and cool, but not like a balloon inflating, more like a loaf of bread rising. Every point in the universe was moving away from every other point. And as it did so, the intense heat and pressure began to fall. Yet, even as it cooled, the universe in these early moments was still unimaginably hot. We're talking about temperatures in the billions of degrees. In this searing cauldron, matter as we know it could not exist. Instead, the universe was filled with a primordial soup of particles, constantly being created and annihilated in high-energy reactions. Among this soup were the most basic building blocks of matter, quarks and leptons. Quarks are the particles that make up protons and neutrons, while leptons include electrons and neutrinos. In the first moments after the Big Bang, these particles were free and unbound, zipping around at near light speed. As the universe continued to cool, something amazing happened. When it was about a millionth of a second old, it had cooled enough for quarks to stick together, forming the first protons and neutrons. This was the dawn of matter as we understand it. But the universe was still too hot and dense for these protons and neutrons to come together and form atoms. That would have to wait a while longer. However, the stage was set. The fundamental particles had been formed, and the universe was filled with the raw materials needed to create everything we see around us today. In these early moments, the universe was also filled with light. But this wasn't light as we know it. It was a seething, chaotic maelstrom of high-energy photons, constantly interacting with the free particles. This kept the universe in a state of opaque plasma, like a fog that light can't penetrate. As the universe expanded and cooled, this fog eventually lifted, giving rise to the cosmic microwave background radiation we can still detect today, but that's a story for another time. These first moments after the Big Bang were brief, but they were incredibly important. They set the initial conditions for everything that followed. The density fluctuations in this early universe would later give rise to galaxies and clusters of galaxies. The balance of matter and antimatter determined the amount of matter left over to form stars and planets. These early moments set the stage for the universe as we know it. As the universe cooled, something amazing happened. Picture this: a mere 300,000 years after the Big Bang, the universe's temperatures dropped to around 3,000 degrees Kelvin, cool enough for protons and neutrons to start playing nice and form atoms. Now, atoms are the building blocks of everything we see around us. So their formation was a big deal, but how did it happen? Well, it's all about energy and forces. As the universe cooled, the energy levels dropped, allowing the nuclear forces to take control. These forces, stronger than any other in the universe, started to pull protons and neutrons together. When a proton and a neutron got close enough, they would snap together, forming the nucleus of an atom. The nuclear forces held them together, but there was a problem. The universe was still too hot and dense for electrons to join the party. So for a while, the universe was filled with these positively charged nuclei, just waiting for their negatively charged partners. As the universe continued to cool, the electrons finally had their moment. They started to get captured by these atomic nuclei, forming the first atoms. Most of these were hydrogen atoms, the simplest and lightest atom, but some helium and lithium were also formed. The formation of these atoms was a turning point. You see, before this, the universe was like a thick soup filled with charged particles that scattered light, making it opaque. But atoms are neutral, so when they formed, the universe suddenly became transparent to light. This is why we can look back in time to this moment, but not before it. This moment, known as the era of recombination, marked a major shift in the universe's development. The universe was no longer a plasma soup. It had structure, it had atoms, and it was ready for the next stage of its evolution. The formation of atoms was a critical step towards the universe we see today. From the simplicity of atoms, complexity began to emerge. As the universe cooled down after the Big Bang, atoms began to form from protons and neutrons. These atoms, primarily hydrogen and helium, didn't stay as isolated entities for long. Gravity, that unyielding force that draws matter together, began to weave its magic. Gravity, in its relentless quest, started to pull these atoms together, creating pockets of dense matter. Over time, these pockets became so dense and hot that they ignited. And just like that, the first stars were born. These weren't like the stars we see in our night sky today. They were massive, hot, and short-lived. But they played a crucial role in the cosmic tale we're unraveling. Within these colossal furnaces, a process called nuclear fusion began. This process involves smaller atomic nuclei coming together to form heavier ones. It's like the universe's own high-stakes game of Lego, building up complexity from simpler parts. As hydrogen atoms fused together under immense pressure and temperature, they formed helium. This fusion process released an enormous amount of energy, causing the stars to shine brilliantly. But the universe wasn't content with just hydrogen and helium. Within the hearts of these stars, heavier elements started to form. Carbon, oxygen, all the way up to iron were forged in the nuclear fires of these early stars. These elements are the building blocks of everything we see around us today, from the air we breathe to the ground beneath our feet. As these first stars lived out their short, brilliant lives, they began to die, exploding in spectacular supernovae. These explosions scattered the heavier elements across the universe, seeding the cosmos with the raw materials for future stars and galaxies. At the same time, gravity was at work again, pulling these atoms together to form galaxies. These galaxies, vast islands of stars, gas, and dust, started to take shape. They spun, collided, and merged, creating the beautiful cosmic tapestry we see today. It's fascinating to think about, isn't it? How complexity arose from simplicity, how everything we know came to be from a dance of atoms and gravity. Each star in the sky, each galaxy we observe, is a testament to this incredible process. The birth of stars and galaxies wasn't just a cosmic event, it was the universe discovering art. Each star, a brushstroke of light, each galaxy, a swirl of cosmic color, and the canvas, the cosmos itself, vast and unending. So the next time you look up at the night sky, remember the journey of those tiny atoms. Remember how they came together, sparked by gravity, to create the stars and galaxies we see today. Marvel at the complexity that arose from simplicity, at the beauty that arose from chaos. Stars and galaxies are the universe's art, painted with atoms and gravity. Fast forward to today, about 13.8 billion years after the Big Bang. The universe has come a long way from that singular point of infinite density and temperature. Now, it's a vast, complex entity filled with galaxies, stars, planets, and a whole lot of nothingness in between. It's a cosmic web we live in, a vast network of galaxies bound together by the force of gravity. These galaxies are strung along immense filaments, separated by voids that can stretch for millions of light years. The universe is not just stars and galaxies, though. In fact, they make up just a tiny fraction of the universe's total content. The universe, as we understand it today, is composed of about 5% ordinary matter. This includes everything we can see or detect directly. Stars, planets, galaxies, even you and me. But what about the rest? Well, about 27% of the universe is made up of what we call dark matter. It's something we can't see or detect directly, but we know it's there because of the gravitational effects it has on galaxies and galaxy clusters. And the remaining 68%, that's dark energy, a mysterious force that's driving the accelerated expansion of the universe. Yes, the universe is getting bigger every second of every day. Galaxies are moving away from each other, carried along by the fabric of space-time itself as it stretches out. That brings us to the future of the universe. What does it hold? Well, based on our current understanding, the universe will continue to expand indefinitely. The rate of expansion is even expected to increase, thanks to dark energy. Eventually, galaxies will move so far apart from each other that they'll no longer be visible to one another. Stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. The universe will become a cold, dark, and lonely place. But don't worry, that's not going to happen for a very, very long time. We're talking about trillions of years into the future. In the meantime, the universe continues to surprise and amaze us. There's still so much we don't know, so many questions left unanswered. What is dark matter, really? What about dark energy? Are there other universes out there beyond our own? The universe is a grand, intriguing puzzle, and we're still just beginning to put the pieces together. Every new discovery brings us one step closer to understanding our place in this vast cosmic landscape. And who knows what surprises the universe has in store for us in the future. The universe continues its journey, ever expanding, ever evolving. The story of the universe isn't finished. As we've journeyed from the birth of the universe to the present, it's clear that the cosmos is ever changing, ever evolving. But what about the future? What lies ahead in the unending journey of the universe? There are several theories about the eventual fate of the universe, each as fascinating as the other. Some scientists propose the Big Freeze, a theory suggesting that the universe will continue to expand indefinitely. As galaxies move away from each other, stars will exhaust their nuclear fuel. The universe will grow colder and darker until it reaches a state known as heat death. This is a future where the universe is uniformly cold and life as we know it will be unable to exist. On the other hand, some theories suggest a more dramatic end in a scenario known as the Big Crunch. This theory posits that the expansion of the universe could reverse, causing everything to collapse back into a singularity, the same state the universe was in before the Big Bang. This could potentially lead to another Big Bang and another universe in an eternal cycle of creation and destruction. Yet another theory, the Big Rip, proposes a future where the universe's expansion accelerates to such an extent that galaxies, stars, planets, and even atoms are torn apart. But, as with everything in science, these are just theories. The truth may be something entirely different. And that's the beauty of it. The universe isn't a static entity, but a dynamic, evolving system full of mystery and wonder. Whether it's the Big Freeze, the Big Crunch, or the Big Rip, or something else entirely, one thing is certain. The universe's story is one of constant change, of transformation and evolution, from a singularity smaller than an atom to the vast cosmos we see today. Whatever the future holds, the universe's story is one of constant change and incredible beauty. What a journey it's been, from a singularity to the vast cosmos. We've traversed the timeline of the universe, from the earliest milliseconds of existence to the intricate cosmic web we find ourselves in today. Our voyage began with the biggest unanswered question: what was there before the Big Bang? We explored the concept of a singularity, a point of infinite density that marked the birth of our universe, an event so profound it set the stage for everything that followed. Next, we delved into the Big Bang Theory itself, a groundbreaking proposition that reshaped our understanding of the cosmos. We learned that in the beginning there was nothing but a hot, dense state which rapidly expanded, creating space and time as we know it. In the first moments following the Big Bang, the universe was a hot, dense soup of particles. As it cooled, these particles began to form atoms, the building blocks of everything around us. This was a pivotal moment in our cosmic history, marking the transition from a universe of particles to a universe of atoms. From these humble beginnings, stars and galaxies were born. We took a cosmic journey from the birth of the first stars to the formation of galaxies, marveling at the complexity and beauty of the universe's architecture. We then looked at the universe today, a vast, ever-expanding cosmos filled with billions of galaxies, each brimming with stars, planets, and the potential for life. And we acknowledge that our journey is far from over. The universe continues to evolve, its story still being written with every passing second. The Big Bang Theory not only helps us understand our universe's history, but also underscores the intricate and interconnected nature of existence. It reminds us that we are a part of this grand cosmic tale, our origins woven into the fabric of the universe itself. The universe's story is our story, a tale of creation, evolution, and endless wonder.